no matter what. That's the run flag. Okay, so in this particular case, we're actually showing you configuring both timers, timer 0 and timer 1, for a certain operation. Right. We've seen how the gate works. So that effectively allows you to disable or enable the run flag. So even though the run flag's saying count, the gate can use it to hold the count temporarily.
You know the bit where we're going to work out like the machine cycles to work
Yes.
out reloading, if you wanted a specific...
Yeah, we're going to do another example in a minute.
Couldn't you just use another oscillator on that pin?
You could, but why bother?
Like say you wanted...
Yeah,
instead of
it's
working
perfectly
out-
possible. You could actually say, I have a clock source, so I've got one oscillator which is from this thing, and then on that pin I could have another oscillator that's accurate, that's feeding in. It's perfectly possible to do it, but it's probably more expensive than just using the one oscillator, and where you need these accurate delays, using something with the timers. We wouldn't normally...
I mean, like, so instead of working out...
Yes, you could do it. You
machine
could do it.
cycles, so-
You could. It's possible. We don't normally do it though.
If you're going to use something else, you just use a real-time clock chip instead.
Yes. Yes. So I wouldn't see. You could do that, and that would be fine. But in most of the kind of embedded systems that we deal with, we wouldn't bother with. You know, provided we've got a crystal that's operating at a known frequency, we can work out appropriate delays and things like that, just from that one source, to a certain precision. Okay, I've kind of told you about all of this anyway on this slide. This is just reminding you about how the flag works. So the flag is triggered when there's a rollover from the maximum value to all zeros. And that's always true whichever mode the timer's in. So there's an example down here, and actually I don't think this example is quite correct. I didn't make this slide. And we're being asked to work out what is an appropriate reload value in order to achieve a certain delay. In this case, a delay of 65.4 milliseconds. Well, the way we've done that is, in this particular case, we're using this crystal, okay, an 11.0592 megahertz crystal, and so it takes this amount of time for one machine cycle, slightly more than 1 microsecond. So what we can do is divide this number into 65.4, and that will tell us what count to use. Okay? So for example, let's if I had a 12 megahertz crystal, and it takes 1 microsecond per machine cycle, if I want to achieve a delay of 1 millisecond, that's 1,000 microseconds, I know that the value that needs to be loaded in there is 1,000 away from the overflow value. And that's where this is slightly wrong, because the person here has done the same kind of thing. They've said, okay, I want to achieve 65.4 milliseconds delay. Well, how many counts would it take to get to that number, given that an individual count takes 1.085 microseconds? So I want to achieve 65400 and divide that into it. That's 65400 microseconds, but a count of 1 takes 1.085 microseconds. Divide one into the other, and you get this number. Where is it? I think it's that number. I don't know which number it is. Let's say it's this this number. So we now need, in fact, it is actually this number in hex. This number. I need to subtract that from the overflow value. Now the way the person who calculated it here is they subtracted that magnitude. Have I got this right? Problem is I'm not working with these things. So if I know how long it takes to do a certain count, I subtract that from the overflow value, and that will be the time it takes to reach the overflow. I'm just trying to work out which of these numbers it is. Right, what it's saying here is if I was to load that initially into the counter, they're saying it would take 65.4 milliseconds until it overflows. But what I'm saying is what's wrong is they're subtracting this from FFFF, and actually technically they should be subtracting it from 0000, because it's not the number of steps to FFFF that causes the overflow, it's the number of steps from the 0, so they'll be out by 1 machine cycle. That's what I wanted to say. So let's say I wanted to achieve this. Let's just do this example, and then we'll call it a day. So this time, I've got an 11.0592, whatever it is, megahertz crystal. So I'm just remembering that 1 machine cycle takes 1.085 microseconds. And I've been told I want to achieve a delay of 65 milliseconds. 65 milliseconds is the same as 65000 microseconds. So I divide this into this to work out what the count is that I need. So I divide that by 1.085 microseconds, which will be a number just slightly less than 65,000. I don't know what the number is. Let's just pretend, because I can't work it out in my head, pretend it was 62,000. Okay? That's how many steps I would need so that to get from an initial point to the overflow point. If you like, it takes that many steps, because each step is going to take this amount. So that times that would give you this figure. I've got to make sure that from the overflow value, all the zeros, I've got to be 62,000 steps away from it. That's my initial point. Because 62,000 steps later, I will get to all the zeros and the overflow flag will be set. So the value I would need to load into my timers to achieve this, you can actually do it like this way. You could actually say, I'm not sure if you can do it as a 16-bit thing, but let's just pretend you can. I think you can actually. Move into timer 1, immediately minus 62,000 decimal. You could do that. Now, I don't know what that number would be in hex, but that would be a number loaded into the 16-bit entity that would take us, to get from that initial value, it would take 62,000 steps to get us to all zeros, causing the flag to overflow.
What was the 65,000?
Microseconds.
That's the delay we wish to achieve. But each step doesn't take 1 microsecond now. Because we've changed the crystal, it takes slightly longer. It takes 1.085 microseconds. Bearing that in mind, I need to know what value to start the timer at in order so that 65 milliseconds later, or 65,000 microseconds later, we will get an overflow. Yeah?
Why does it take 1.3?
Because the machine cycle that's used for determining how fast instructions go is in the 8051 a 12th of the oscillator frequency. And whoever's wired up this circuit has chosen to use that crystal, not a 12 megahertz crystal. They've used basically an 11 megahertz crystal. So that's why there's the difference there. So what I'll do next week, I'll go through very precisely an example like this, where I've done in the calculator what the actual numbers are to show you a work example of achieving a particular delay. So we've got how many more slides? There's a couple of programming examples, a bit of code, and that's it. So we should easily finish this on the Wednesday of next week, and then we'll be moving on to interrupts. So have a good weekend.
Thank you.
You know what I was saying about the extra second oscillator?
Yeah.